We just have this last bit about looking at the difference spatially between the primary sigma bond and the secondary pi bond. So hopefully if you were given the structure, you would say, with regard to the carbon atom, what sort of orbital hybridization do we have? Make an sp2. I'm kind of liking that because we have 3 sigma bonds, no lone pair electrons, so sp2. Great. So what sort of structural geometry? Trigonal planar, bond angle, 120. Yep. So, of course, PM stands for picometers. Maybe, maybe not. Okay, so which bond is shorter? This double bond between the 2 carbons or the single bond between carbon and hydrogens? Which one's shorter? Yeah, this one. This sigma bond's shorter. Now, usually a double bond is shorter, but this is between 2 carbon atoms. This is between carbon and hydrogen. So we're kind of comparing apples to oranges in a way. So the fact that this hydrogen atom is small kind of made this, I think, it's small. But usually your double bond is the same. Always, if your double bond, it's the same 2 atoms will be shorter. Not sure. I think I made these. Let's see. Uh-oh. Maybe I didn't do these. That's okay. Sorry, I didn't do this little video. I did some other videos. So this is ethylene. We have the nucleus of the carbon atom, nucleus of the carbon atom. It also looks like an X-ray image, doesn't it? We have nuclei of the 4 hydrogens. So those would be, you can kind of see the overlap here between the atomic orbitals to make the bond orbital. That would be your sigma primary bond. And then over here, remember your pi bond will be in the, and we're going to see some figures here, that basically the unhybridized p orbitals of the carbon atom create this region of space where the 2 electrons will kind of buzz above and below the plane of everything else. And so this actually is a combination. You kind of see the ghosty sigma bonds back there, and you can see your pi bond cloud. So nuclei of carbon. This is showing you the hybridized orbitals. The sp2 hybridized orbitals are here in gold. There we have unhybridized p orbitals from the 2 carbons. So that overlap, or this area up here, I know it's like, how did that overlap? I don't really know. But that's actually where your pi bond, your electrons creating the pi bond are going to be. So again, here we have sigma, 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 pi. So I have some, this is actually kind of what I've been saying, or what I've been talking about. The sigma bond, or the primary bond, think of it as connecting the nuclei of the atoms. They're going to be connected. Then the pi bond kind of takes what's left over, kind of above and below. So many words is what we talked about earlier, but again, just this afternoon. Again, this is, this is any generic alkene. In chemistry, a lot of times you'll see this R group, okay? This R group could be anything. It just means something generic. We have 2 different R groups, R and R prime. But this is talking about the carbon sigma bond, pi bond. So this is a double bond right here. Taking it up a notch, triple bond. So carbon triple bond with a hydrogen on either side. This is acetylene. Of course, what sort of orbital hybridization do we have for the carbon atom? Like an SP. What sort of structural geometry? Linear. Yep. Bond angle? 180. 2 or 1. So let's kind of take a look at what that looks like. So you told me sp orbital hybridized is what that carbon atom has done. So again, in gold here, these are the hybridized atomic orbitals that we're going to have overlap with the other carbon atom and the hydrogen atom. So here we have the unhybridized p orbitals. These 4 lobes here can then create the 2 pi bonds that are associated with the triple bond. So here we have carbon, carbon. You see the sp hybridized orbitals, kind of the gold-looking things. Okay, then these lobes here are going to be locations where electrons reside, participating in that pi bond. Looks like this. Carbon, triple bond, carbon. Single bond hydrogen, single bond hydrogen. That's it. I got home and Carl, my husband down at the West Burlington campus, is teaching this class about the same timing. And I told him where we stopped on Friday. He's like, you could have finished that. I'm like, I know, but I didn't want to. Okay. It's my class. He's funny. That's okay. So, you know what comes next? Unit 5. I run into some problems with the topic of gases, and it goes something like this. It's kind of the opposite of, remember when you did that thermodynamic unit where in high school maybe you did cover thermodynamics, okay? The Q is equal to MC sub P delta T. Well, in high schools, and I can understand why, because gases, everybody loves the topic of gases. In high school, you probably did cover gases. And so the tricky part for me is keeping it interesting, adding to what you already know. Another topic that actually in general chemistry too that is more severe than this is the whole acid bases thing. In Gen Chem 2, we're going to have to wait till we talk about chemical equilibria before we can talk about acids and bases. And that's an uphill battle too. So just hang with me, kind of connect what you know about gases and what's new about gases. So the one thing about gases is that if you remember the kinetic molecular theory, the old idea that solids have least amount of motion, high degree of intermolecular bonding. Liquids have a moderate degree of intermolecular bonding, more motion than solids. Gases are just all over the place, okay? So my favorite way is I draw a lot of boxes with the topic of gases, okay? So I like to understand a gas, usually you have to confine it. So I'm going to confine our gas particles. These gas particles, I'll give an arrow at least to one to kind of show you that it's bouncing around. So they're my gas particles. So I thought about this list of what gases do or are, and it's almost like, it's so cool. It seems like you could say, turn it around and say gases are incompressible and see which one of these you thought was wrong. Anyway, these are all right this time. So gases are compressible. You buy compressed air, right? Okay, that compressible just means I could take this box and squeeze it. Okay, you can't take, for all intents and purposes, you cannot take a liquid and compress it. You can, but not nearly as easy as the container of gas. Gases are compressible. Gases will always take the volume that you give them. Okay, so gases will expand to fill the entire volume. So, and part of that totally makes sense to me. Like if this was sealed up, right? And let's say it had some deadly gas in it. And what if I were to go ahead and fracture it? These have kinetic energy. These are bouncing against the walls of their container. Little by little, they are going to, diffuse out, okay? They will take on the shape of their container. If they have no container, there they go, okay? So I think that's pretty cool. Close up that deadly gas. All right, it's been a while, but we talked about densities. Densities, remember, density is a ratio of mass to volume. So what you do is you isolate a liquid or a solid or gas, you get its mass, and you divide by its volume. Now, the fact that gases are compressible, guess what? That is a moving target. I'll put the sign delta there. You can change the volume until the cows come home. So that means that your densities are variable too. Gases have relatively low densities. Makes sense. They have a lot of space between their particles compared to liquids and solids. Gases want to mix to form a homogeneous mixture. So I could take this box A and I could take this box B and I can make a little conduit between the two. And if I give enough time, kinetic motion, the motion of those gas particles is the A and the B would intermingle. Okay. So they're team players. They are just wonderful little particles. So we're going to spend a little bit of time talking about this idea of pressure. I kind of drew this particle bouncing up here, and we're going to talk about how it's a punch. Literally, it's a punch. It has an amount of force, and it's going to punch. Now, granted, it's just one particle. It's not going to be that big. It's going to punch a certain amount of area. And the ratio of force per area gives us pressure. So that's kind of fun. Punch. They're so awesome. So when we get rolling doing problems with gases, you probably already know this, I know. But we are going to need to fully describe a gas. We're going to need to know the pressure. We'll talk more about the pressure. The particles are exerting against their wall. We're going to need to know the temperature at which those gas particles are hanging out. We're going to need to know the volume that's containing those gas particles. And anybody, yeah, it's already up there. The variable N, that means moles. We're going to need to know how many gas particles are in that volume at that temperature creating that pressure. So these four things will tell us basically all we need to know about the gas. One of the things I think is so cool about gases is notice one of the things I don't need to know is which gas it is. That could be carbon dioxide, that could be nitrogen, that could be argon, that could be liquid methane, or not liquid methane, that could be gaseous methane. And they're all going to behave interlocking with those four quantities will be related in the same way. That is so cool. Oh my gosh, gases are just so cool. So pressure is an important player. Pressure is kind of the punch, the force it has over a given area. So we could calculate the pressure of anything if we take the force, the punch, divided by the area over which that force is applied. Something that's helpful is to kind of think about the gases here in this room. You guys have told me most of it's nitrogen gas. Okay. And the gas particles in this room exert a certain pressure. And some of you may know if you climb a mountain, what happens to the pressure? It decreases. Yeah, you climb a mountain, pressure decreases. You can almost kind of think of it this way, as if you climb a mountain, basically you are taking off that much. That would be right. You have less of a column of air. So the way it turns out, you've probably heard of PSI. PSI stands for pounds per square inch. When we inflate our tires, we're looking for 65 or so, what PSI, depending upon your tire. So pounds per square inch. As it turns out, the nitrogen-oxygen 80-20% mix gives us a punch about the mass of a bowling ball, which is 14.7 pounds. And I think this is quite clever. Your thumbnail is about a square inch, pounds per square inch. So this looks terrible if you ask me. So you take a bowling ball and you set it on your thumb, and that's about, as we are interacting with the Earth's atmosphere, that the pressure of that, the gas particles in the atmosphere collectively bang against us. Isn't that cool? 14.7 pounds per square inch. I just think that is so cool. It's just me, I guess. So pressure is force divided by area. Now, The reason we're seeing kind of the green and the pink is they both have the same masses. So that means they have the same force that is acting upon here. But which one has the bigger area? The green or the pink? The area interacting with the surface. So if I could take my marker worked, which it used to work, it stopped working again. If I could take a circle here, take a circle here, which one has the bigger area? The pink. So can you see where if you increase the area, what happens to the pressure? The same force over a larger area gets smaller. Yep. Yep. So this is an example. You can almost feel it. Like if I was a super ant and I could stand a little bit of open, I would rather be under this one than under this one, because the force is greater under this one. Speaking of ants, so an elephant is quite massive. So pressure is force, which would be basically gravity acting upon the mass of the elephant. You figure if it's standing, it's got all 4 feet on the ground, its mass is being distributed on 1, 2, 3, 4 feet. Okay, so we can calculate the pressure that's being exerted at those 4 locations. Now this is interesting. And it seems like in Chem 2 we talked a little bit about this too. But there is more actual pressure being applied at the location of the blade of the skater than there is being distributed on that elephant standing on all 4 feet. Because the area of that blade is very small. As we make this smaller, guess what? The pressure increases, right? One of the things about increasing your pressure is we can increase, and she's doing it, we can increase the pressure to the point where, must be, yeah. We increase the pressure to the point where actually the solid turns to a liquid. So if you've ever heard this before, actually under the blade of an ice skater, he or she is creating a track of liquid, which is actually part of the physics of the skating. All right. Okay, I know this isn't physics. So one of Newton's laws is force is equal to mass times acceleration. And you don't have to know this, but a good unit of force, because we aren't going to be worried about force as much as pressure. Okay, we're going to kind of just absorb this into the pressure of our gases here in a minute. But since force is mass times acceleration, kilogram, of course, is a great mass, and meters per second squared is a great acceleration. So Newton's breakdown is kilogram meters per second squared. Again, you're like, oh. So force, which Pascal is a great unit, is equal, pressure, which Pascal is a great unit of pressure, is equal to force in newtons divided by area, meters squared. But instead of Pascal's, quite frankly, we are going to, let my pen work. We're going to focus a lot on atmospheres and millimeters of mercury. Those are probably the 2 most obvious ones. See, it did work and then it stopped. Okay. So if I could put a star here, I would. See, it works that way. Oh, goodness gracious. So put a star up there. You're going to want to memorize that. 1 atmosphere, remember we used the word exactly, is exactly equal to 760 millimeters of mercury. And I'll kind of tell, of course, millimeters is a height or a length. We'll talk about why that is. We don't use these as much, pascals or kilopascals or bars. You don't have to memorize that relationship. If you need it on a test, I'll give it to you. And there is our 14.7 PSI, pounds per square inch, that we talked about with the bowling ball on the thumbnail. This is an approximate relationship. We have a cold front coming through, so the barometric pressure is falling right now. So that means literally, like you might think it does, those nitrogen particles are collectively nitrogen, oxygen, because they all kind of work together. All the gas particles in the atmosphere are giving less of a punch. The pressure is lowering. So anyway, what I'm starting to say is under normal sunny day, atmospheric pressures is the pressure of 1 atmosphere, the gases in the Earth's atmosphere. At sea level, okay, around about 1 atmosphere, 760 millimeters mercury, 14.7 pounds per square inch. This one you might also want to memorize. I know you probably, it seems like you should have some homework, which I haven't done this unit's homework yet. But these problems are more fun than the structures, I think, personally, so they should be fun. 1 millimeter of mercury is exactly equal to 1 torr. And then, so I put a star next to the millimeters mercury and torr, but not a star next to this one. 1 bar pressure is exactly equal to 10 to the 5th pascals. All right. We used to have a few of these in the chemistry lab, which I don't know why you need more than 1 in a room at a given time. But if somebody says that they measured the pressure of the atmosphere, Earth's atmospheric pressure, using a mercury barometer, this is what they used. Of course, mercury is one of those few elements that's a liquid. So the way a liquid mercury barometer works is it's kind of dangerous. There's actually an open pan of liquid mercury that's open to the atmosphere. And the other part to a mercury barometer is the glass tube. So the glass tube needs to be closed at the top, and what they do is they pull a vacuum on it, so no gas allowed. And then I picture myself as them putting their finger over the open end, and then, sounds dangerous, and then basically slipping the evacuated tube that's closed at one end, slipping the open end into the liquid mercury. Then what happens is sort of a kind of an equilibrium, kind of a flux sort of thing. That liquid mercury actually will be beat upon in the open pan, and it will go up the column. So the way this works then is to know what the pressure of the atmosphere is what the pressure of the atmosphere is. What you do is you measure the distance that the mercury went up the column. Okay. So when it says 760, I had my zoomer up here, 760 millimeters of mercury, I think I might take it back. That's what 760 millimeters is what, 76 centimeters? Okay, so 76 centimeters is. Okay. But that's what they're talking about. That's a mercury barometer. So mercury does pretty well. Okay, you can kind of see this is a mercury barometer. It's closed at the top, vacuum pulled. Again, the 760 millimeters mercury, which is about 31 inches or so. That is the distance right here between the bottom of the mercury, how far up it goes. Mercury works well because it's so dense. Now, here is, instead of a mercury barometer, I thought this was clever, this is a water barometer. Water can do it too. But notice, since it's not as dense, we had to actually then account for that by the water is going to have to travel up farther to show the same pressure. Get the same pressure on both of these. So I thought that was kind of cool. Not only farther, but 34 feet? Not a very practical barometer. So I'm going to kind of talk you through the concept of barometer and kind of think through what that means or how gases kind of interact with this sort of simple device. What's wrong with this mercury barometer? The top's open, yeah? If the top's open, it won't work. So here we close the top. Yep. And again, we would measure the distance from the bottom of the liquid up the column. That's what's going to be our 760 millimeters. Okay. By the way, if you are a weather junkie, they'll say what the atmospheric pressure is oftentimes in inches. And this is what they're talking about, the inches, how far up your mercury has traveled. All right. What's the difference between this column and this column, this barometer and this barometer? Yeah, it's closed, right? So what's the difference? Yeah, there's more glass here. But to me, and I'm trying to double check, it looks like they went up the same height today. It just has more glass. Well, with that in mind, what do you think's wrong with that mercury barometer? It's too short. They didn't give it enough room. They pegged it out. Sigh. Yes. Okay. This is a figure, and in this class, in General Chemistry 1 and 2, you won't need to use one of these. I use one of these in some of my other chemistry endeavors, but it's called a manometer. And it's great for measuring gases. Do you guys remember with our burettes? What, if this is a burette stopcock, what would you say about, is it open or closed? What do you think? You guys remember? It's open. I guess you guys haven't done too many titrations, but that's, remember, if you remember your burettes, you guys had your stopcock. And if it was perpendicular, that meant it was totally off. If it was parallel, it was totally open. So it's parallel, it's totally open. Yep. So what manometers are great at doing is to have a gas in this chamber. This is liquid mercury that can kind of move with responding to this gas. I'm going to show you a couple different scenarios. In this scenario, actually, it's like a barometer where there is a closed vacuum here. So does this make sense? Can you see where the pressure of the gas is displacing the mercury back up? In this case, actually, the pressure of our gas is greater than atmospheric pressure. Pressure of our gas can be calculated by this H right here. All right, so here's another scenario. Notice you can't tell the difference, but they've marked it. So this one's open to the atmosphere. And in this case, again, we have our gas pushing on our mercury. Okay, assuming that's a positive, not a negative pressure here. And in this case, actually, the fact that they're equal, oh no. Huh, okay. Now I can see it. Can you guys see this here? Does it look to you like it's drawing a vacuum, like a straw? Actually, this is happening because the pressure of your gas, your pressure of interest in your chamber, is less than the pressure of your atmosphere. Does that make sense? So down here, we could do a little calculation, and we can calculate the pressure of our gas by taking the pressure of the atmosphere and subtracting basically the height that it went down. Isn't that cool? Actually, I have one more scenario, and I double-checked with my husband in this last scenario, and wrong. Wrong. OpenStax. OpenStax has two wrong figures in this part. Can you see where actually, again, it's open to the atmosphere, but doesn't look like it's blowing? It's like it's blowing instead of sucking. Because you can see the mercury is displaced up. So in this case, the pressure of your gas is greater than the atmospheric pressure. And what it should do is, should be able to draw on this, but what it should do, this is my glass, and I have mercury here. Okay, the height should be this height right here. That should be what they're calling the, well, yeah, that should be your H instead of how they marked it. So don't blame me. But yeah, so this would be a case where the pressure in of your gas is greater than the pressure of your atmosphere. Mercury is great at not, it's relatively inert. It's nice and dense. It pushes and pulls and. Okay. So these four things, in any experiment, what we like to do is we like to, what we say, isolate two. These are all four variables. So we like to take them two at a time. So I'm going to walk you through taking them two at a time. The first two I want to look at are pressure and temperature. So these two. Now this is going to assume that the other two are what we say held constant. So I'm not going to mess with my volume. I'm not going to mess with my number of moles. But these are very intuitive. What happens to, if I take the temperature and increase it, what's going to happen to my pressure? They're going to go faster. So what happens to my pressure? Temperature goes up, pressure goes up. Exactly. And so there's another mathematical symbol we haven't run into yet here, but it's called, instead of an equal sign, it's a proportionality symbol, which to me, a proportionality symbol looks like infinity with a bite taken out of it. So we say if temperature goes up, pressure goes up. Temperature goes down, pressure goes down. And if you've had like a latex balloon that you've gotten on a cold day, take it to your car, temperature goes down, and actually it's just not as hot when you go out. And actually, all right. A couple little videos. They're pretty adorable. Hope that's not too loud. Low tech. So we have the gas of interest here in this round bottom flask, and this is our gas gauge. And we are going to heat it up in a water bath. Heat up our gas in a water bath. So what happened to the gas gauge? It's going up. Heat it up some more. Gas gauge goes up even more. Pretty straightforward. I wonder, did they add more water or did it just boil up? No. Now, some of you guys, and I'll make a note on here, already know this if you've kind of dabbled in this sort of problem, but your temperature is always going to have to be in units, always, I think, in units of Kelvin. And it seems like we talked about the 3 different temperature scales, Celsius, Fahrenheit, but of course Kelvin is a kickoff of Celsius. So if we're looking at the Celsius and the Kelvin temperature scale, I don't know if you guys remember this, but they differ by 273.15 units. Here, since we have no decimals, they should be all offset by 273. They didn't look like it. Now that doesn't look right either. Are you serious? Holy Kalodi, OpenStax. Because 0 Celsius is 273 Kelvin. Grrr! I don't know if they're just being jerks about this. And 100 Celsius is 373. It's so frustrating. But what they're trying to show you is that as you, let's see if we're going down, as you increase the temperature going down, you're increasing the pressure. And you know we like to plot things. So here's a plot. Along the y-axis we have pressure, along the x-axis we have temperature. So these would be normal temperatures and pressures of gases. And then what we like to do is we like to take normal, and it's called, let's see, extrapolation, interpolation. It's called extrapolate. We like to extrapolate. So we like to take it backwards to a temperature that's not so normal. What is 0 Kelvin? Absolute 0, yeah. So if we extrapolate that data backwards, what pressure does a gas have absolute zero. Has zero pressure. It's just bizarre. Absolute zero is a bizarre place to go. Okay, so that was pressure and temperature. Now we're going to look at pressure and number of moles. And I'm going to go ahead and keep temperature and volume the same. To me, this just screams balloon. Because like when you blow up a balloon, what are you doing? You're increasing the number of moles in your thing. Okay? Now let's assume that you have maxed out at the volume, so it can't get any bigger. Okay, now when you keep blowing in, you increase the number of moles and you're going to increase pressure. Increase the number of moles, increase pressure. So we're going to use the proportionality symbol again. We're going to say that pressure is directly proportional to number of moles. Makes sense. I think I even have a little video to convince you of this. Like you really need convincing. Looked at because we looked at we're picking on pressure, aren't we? We looked at pressure and temperature, pressure, number of moles. Now we're going to look at pressure and volume. And if you go back to your balloon again, if you take your balloon that's a certain volume and you squeeze it, you reduce the volume. You reduce the volume, what happens to the pressure? You increase the pressure. Yeah, you're squeezing it. So we can't, we're going to use a proportionality symbol again, but we can't, they aren't directly proportional. They're what we say inversely proportional. Because the other two things we looked at went up, went up, went up, went up. Okay. In this case, you see my idea of the balloon. You decrease the volume, you increase the pressure. What happens if we increase the volume? Yeah. So they're inversely related. So what we do mathematically is we use the proportionality symbol, but to show that they're inversely proportional, we say that it's directly proportional to what we call the inverse, or 1 over. So volume is proportional to 1 over pressure, inverse of pressure. Okay, so mathematically that works out well. Problems and doing experiments with gases is, where is your gas of interest? So I'm going to show you a few slides and I'm going to point out where your gas of interest is. This is just an easy syringe. You can kind of see the stock of the syringes here. So our gas of interest is right up here, okay? Notice that the gas can't go anywhere, and on the end of this little syringe, we've got a kind of an easy sort of pressure gauge, okay? So of course that plunger can move in and out. So here we go. So we did some experiments, and notice that with, let's see, how much volume would you say? I'm like in, if that's 10 and that's 15, what, maybe 12 and a half? Maybe 13 milliliters? So 12 and a half or 13 milliliters. I just look at that order there. We're right about there. Okay, and we picked off the pressure. Notice here we must have like pushed the plunger in with a smaller and smaller volume, and the pressure went up. Here we must have withdrawn the plunger, creating more and more volume, and the pressure went down. So that doesn't look very linear, does it? Kind of looks like a snow. But if you go ahead and leave volume here, but plot the inverse of pressure, that looks like this. And this makes scientists happy because it's a straight line and they can infer all sorts of things. So if we plot volume versus the inverse of pressure, we get a straight line. So now as volume increases, the inverse of pressure increases. That's the inverse of pressure increases. Here's another example. So this was the first graph we saw with simply pressure and volume. And if you have your slides here, you can change this to, we again have volume along the x-axis, and along the y-axis, it's 1 over pressure, just like the caption says. Okay, so this V should be volume and 1 over V. Sorry. It's like they've done so well up till now, and gases are such a gases. I think that was the last mistake. I didn't catch that temperature one. Okay. So again, this is back to the syringe. The gas of interest here is trapped with the plunger in the syringe. It's capped off, but this is a little bit different. What you're going to see is that for the plunger, basically we're going to add weight into lead, in the form of lead shot, into that plunger. And as we do that, of course, gravity is going to work on the weight, create a force going down, and it's going to make a smaller and smaller volume. So, in fact, then, the pressure of the gas is going to be related to the amount of shot put in there. So with no shot in the cup up there, you're looking at a volume of 14.3 milliliters. Okay, so actually this right here, our gas of interest, is running a pressure of 1 atmosphere. Notice what we're plotting here is the mass of the lead shot we're going to put here versus the inverse of volume. And again, the lead shot can be a function of the pressure of the gas. All right, so now we put our first bit of lead shot in there, 500 grams. The plunger goes down. What happened to the volume? The volume decreased, and the inverse of the volume increased. Does that make sense? So volume down, 1 over volume goes up. So that was 500, here's 1,000. Okay, yep. So we put more shot in here, 1,000. And notice here the volume decreased, the inverse of the volume increased. I have 2 more points. Oops. Great. These are some of my favorite ones. Hopefully you guys might call this, like, it looks like an Erlenmeyer flask, okay? But it's a fancy Erlenmeyer flask. If you can see it, the glass is thicker than the ones that we generally use. So it's a thick-walled Erlenmeyer flask with a side arm. And the reason it's thick-walled is so it can stand up against pressure, vacuums, and positive and negative pressure. And the little side arm here is so that we can draw vacuum and actually add gas particles to it, etc. The gas of interest, oh my goodness, it's hard to see. So the gas of interest, you can see the syringe is pulled up to like the first gradation right there. So the gas of interest is right here. So we're going to take a tire pump and we're going to pump her down. Before we pump her down, notice we're going to go ahead and cap it off so that we seal the system. So I'm going to go back and forth. This is the first one, increase pressure, increase pressure. So what happens if you increase pressure to volume? Increase pressure, decrease volume. Yep, I think I have one more. Okay, yep, we can continue to go ahead and increase the pressure, decrease the volume. Well, here's one for you. Same setup, cute little marshmallows, minding their own business. The gas of interest is the gas particles in the marshmallows. So again, we've got this. In this first case, what we're going to do is we're going to draw a vacuum. Yeah. So we're going to draw a vacuum. So we're going to decrease pressure. So what should the volume do? Increase volume. So decrease pressure, increase volume. Just makes you smile. So that's drawing a vacuum. Increase pressure, increase volume. So now we're going to disconnect our vacuum pump and we're going to hook it up to a tire pump. So now we're going to, instead of decreasing the pressure, we're going to increase the pressure. So what should that do to volume? Increase the pressure should decrease the volume. They want to have less calories. Just saying. So I didn't do it on purpose, but there it is. These will be due, we'll go ahead and make these due Friday. I think they're pretty harmless. I didn't look at them yet. Oh, but for 10 extra points, you can turn them in Wednesday. But otherwise, it'll be Friday. The games we play.